So our next speaker is Jinyi Yang of the University of Arizona, talking about exploring reionization-era quasars, study the early history or the early SMBHs at Redshift 7 with Keck NIRES. So take it away, Jinyi.
Thank you. I'll just share my screen. Can you see my slides? It's okay. Okay, thank you. Hi everyone. Thanks for the opportunity. I'm Jinyi Yang, a postdoc at the Stewart Observatory, University of Arizona. I'm working on Redshift Quasar Survey and also follow-up works to study the quasar properties. So today I will talk about my recent work about study the early supermassive black hole at redshift around 7 using the near-infrared spectroscopy, for example, from Keck NIRES. So first of all, this reionization-era quasars typically means quasars at redshift above 6 or above 6.5. So since quasars are very luminous, so with these very distant quasars, we can get very important information about early supermassive black hole host galaxy or black hole host coevolution, and also the information about IgM or to the large-scale structure at the early universe. So that's why we want to search for these high redshift quasars. So our group carried out a new Redshift 7 quasar survey since 2016. So far we have already discovered 40 quasars at redshift 6.3 to 7.6. So we can see the left figure, this one shows the magnitude of redshift distribution. The red point from our new survey, and also compared to some published quasars. So this is a quasar redshift above 6.5. And also the right one shows some examples of quasar spectra. So more details of our survey can be found in these 3 papers. So after we build up a sample of new quasars at redshift around 7, so we are doing the multi-wavelength follow-up observations of this quasar sample to try to study the quasar probabilities, study the quasar properties. And then, so one important thing is about the near-infrared spectroscopy, which will directly provide us with the black hole mass and black hole mass growth. So actually, we try to study the high redshift supermassive black hole. We actually want to understand these 2 questions. One is, how did this high redshift supermassive black hole grows to such massive black hole in a short time? And also, the other one is how massive these black holes could be. So we can see in this figure. So this corner is to observe the high redshift quasars. They provide very massive black holes at the early universe. And we can see the other side is some possible seed black hole models. So between them, they're just a few 100 million years. So the question is how they grow to such massive in short time. So its connection between these 2 is still unclear. So we try to use a larger sample and high redshift quasar sample to place more constraint on the supermassive black hole growth and also seed black hole. So to reach this science goal, I'm just collecting the near-infrared spectra. So far, I've already got 33 quasars and at redshift 6.3 to 7.6. So they're mainly from Keck NIRES, Gemini, Jinyi, and also RBT, Magellan, and VRT. So there's an example. Here is example spectra of a redshift 7 quasar. So it's from Keck NIRES. So we can see the broad emission line, also the polar continuum of quasar. And with a near-infrared spectra, we typically just measure in fitting the maximum 2 line and using the maximum 2 line wise to estimate the black hole mass. So using this method for our sample, we have already got the black hole mass, volumetric luminosity, and also Eddington ratio. So we can see in these 2 figures. So the black hole mass in our sample are in the range of 10 to 8 to 10 to 9 solar-mass. And then we will get Eddington ratio. We can see distribution in the red figure. So the mean value is around 1.1 and also the peak is on 1. So and also we can see in the left figure is located around the line of just Eddington ratio around 1. So this result is consistent with some previous works that just suggested that at high redshift, this high redshift quasars have Eddington ratio around 1 and higher than the low redshift quasar sample. So we can see in this figure the black point. The red squares from our new measurement, the black points are from the redshift 6 sample, and also the gray point and the contours are from the SDSS low redshift quasar sample. So as we know, recently there are also some different results that suggest at high redshift there are also some high redshift quasar with low Eddington ratio, so which is affected by selection bias and also the luminosity range of the quasar sample. So since our sample just focuses on the luminous end, so we get a high Eddington ratio of our sample. So after some basic measurements, we also can use this black hole mass to study the supermassive black hole growth. So the left figure show the supermassive black hole growth tracks. So we can see this different color solid lines means the different seed black hole is different seed black hole mass from 100 to 10,000 solar mass. So and we can assuming Eddington accretion and also radiative efficiency around 0.1, and also we assume that this seed black hole started to grow since redshift 30, but we know it should be later. And some of the red point here are from our samples from observation. So you can see our sample, the zoom in panel here, the observation could constrain the seed black hole mass. Now we can see the result. So most of the supermassive black holes in our sample, they require around 1,000 solar mass seed black hole at redshift 30. So as I mentioned, if the seed black holes started to grow later, then they require a higher seed black hole mass. On the other hand, if the seed black hole started with a less mass seed black hole, then we will need a super or higher Eddington accretion or the very low radiative efficiency. So this is what we learned from the sample, and I want to mention some interesting individual within our sample. And this is a new quasar, Redshift 7.5, discovered with German engineers and also Keck NIRES. It's named as, it also has a name, Poniova Anna. So we can see this spectral is the combine of the Keck NIRES and German engineer spectral. We also get a magnitude 2 line here, and using the same method, we will get a black hole mass. So what we can learn from this quasar is, so first we can see this figure. So it's located around the Eddington ratio of around 1. So it's consistent with other quasars in our sample. But this one holds a very massive black hole. It's 1.5 billion solar mass black hole, which is 2 times more massive than the other black hole at similar redshift. So based on this result, this new quasar requires the most massive seed black hole than any other known quasars. So it's 10,000 solar mass black hole at redshift 30. If the redshift 15, it should be 300,000 solar mass. So you can see in this figure, this is the black hole growth tracks, the purple solid lines from this new quasar. So and also compared to the spherical model of the seed black hole. So this result is more consistent with the direct collapse black hole seed model. We cannot rule out any models, but we just say this new quasar is more consistent with the direct collapse model. And also, more recently, oh, sorry, I just cannot, oh, yeah. We get the other one. So the other new quasar at the high redshift and hosting even more massive black hole. So the red solid line here. So this one is again, so challenging the growth model and also more consistent with the direct collapse. So these two 7.5 quasar just prefers the direct collapse black hole seed model. So, and this is what we can learn from the near-infrared spectroscopy and about the black hole mass and black hole growth. And in addition to the black hole growth part, if we combine the near-infrared data and with our multi-wavelength data, for example, the optical or 7 millimeter, we can also constrain the black hole host co-evolution at the early universe. And the other one is we can measure the quasar proximity zone size and try to constrain the quasar lifetime and supermassive black hole growth. Yeah. Thank you.
All right, thank you, Jinyi. So we have time for a very brief question if anyone has one in the Q&A. So one I'm seeing right now, are there plans to find obscured quasars?
Yeah, this is a very good question. Yes, currently our quasar show here is just a type 1 quasar. Yeah, there are also some survey try to use near-infrared or deep near-infrared, or for example, just twice detected quasar. That could help us to selected high redshift type 2 obscure quasars, yes. And also within our sample, we also have few very right, that's the reddened quasar, yeah. It's a very important part of the quasar survey.
Great, thank you very much. And as always, we can continue the questions in Slack.